So my overview on state of materials design is from the perspective of both my day job at Northwestern, the activities of our materials design company, Questec, and of course the current context of all of this is the National Materials Genome Initiative announced by the President back in 2011. And this is to build out the system of fundamental databases and tools that would allow us to take what is currently a 10 to 20 year full materials development cycle and compress that by at least 50%. Now, the White House white paper is not necessarily what I would recommend to understand clearly what is meant by the materials genome. What I do recommend is the National Academy study of 2004, which was on the acceleration of materials and process technology, and specifically addressed what have become the goals of the Materials Genome Initiative. This report reviewed the best practices in place in industry for this kind of materials acceleration technology, and then went on to predict what it is, what are the opportunities, where should we go, and it actually, in that context, discussed the Human Genome Project as the biggest engineering database in history that was created not to support just the life sciences, but to support science-based medicine. And so the analogy was to build out a similarly fundamental database system to not just support material science, but support the science-based engineering of materials. So I think this report gives a pretty clear concept of what is meant by this genomic metaphor. And the recommendation went on to recommend specifically what actually did happen for the Office of Science and Technology Policy to organize a multi-agency initiative that would not only be the building out of this fundamental genomic database system, but the methodology and infrastructure, both for research and education. The highest achievement so far in this technology was 5 years ago, with the first flight of stainless landing gear steel designed at Questec. This represents the first stainless steel to meet the mechanical performance requirements of aircraft landing gear and thereby eliminate toxic cadmium plating. But more importantly, it represents the first fully computationally designed and qualified material. This represents a certain maturity of this technology, which is acknowledged by the timeline here. There's a lot of debate about what a materials genome could be. It's quite clear that the genome we have is represented by this bottom line of the CalFAD system of fundamental databases of phase-level attributes, whose origins can be traced back to Kaufman and Cohen in the 1950s. It grew to be an international organization in the 1970s under the name of CalFAD, and led to a number of small businesses and commercial software and database systems. It has evolved beyond simply solution thermodynamics to expand to many phase-level attributes, including atomic mobilities, atomic volumes, and even elastic constants. It was originally based on empirical measurements, but as the accuracy of DFT quantum mechanical methods has improved, DFT has become an equal partner in contributing the fundamental quantities that go in to those assessed databases. Under CalFAD, it's been well developed for inorganic materials, but really there's a parallel activity in organic materials that's as old and almost as well developed at this point. It was the appearance in the early 1980s of the thermocalc software, commercial software, and the European-based SGTE database standards that gave a new level of accuracy to this technology, and that inspired our founding in 1985 of our Steel Research Group Design Consortium that built a practice of computational materials design that was specifically structured to make use of this fundamental data system, beginning with steels, acknowledging that steels are still the materials for which we have the deepest and most quantitative scientific understanding. That led to a number of commercial steels that are now in the marketplace and further developed by our company Questech. It was founded in 1997. Throughout the 1990s, a number of demonstration projects were done at the university to demonstrate using the same methodology in ceramics, polymers, and composites as well, showing that the approach to design is as general as the supporting fundamental database structure. It was the successes in design in the 1990s that helped make the case for the DARPA AIM initiative in 2001 that really began what is now called Integrated Computational Materials Engineering, or ICME. And this really built on that design foundation to address that full materials development cycle, which includes process scale-up, process optimization at the component level, and ultimately the quantification of manufacturing variation to specify minimum properties that a user can specify in system design. That was very successfully demonstrated first in nickel-based turbine disc alloys and has moved on to other applications. But in fact, all of these success stories at this level so far are in metals, but with the demonstrations of the breadth of applicability of the foundation underneath it, we are quite confident that the methodology that's been demonstrated in metals at this level is the methodology we will use to deliver all classes of materials in the future. So at this point, we've had a bit more than a half century of evolution of the underlying database system. We've had a quarter century of a design practice and only an eighth century so far of putting this whole process together to get a new material to an application more quickly. That Steel Research Group in its current form has the recent participants summarized here. Just say that it's been a collaboration of government laboratories, university, and industry representing the perspective of not only materials science and engineering, but materials users and materials suppliers. Foundation of the approach is in the writings of the late Cyril Stanley Smith, who wrote extensively about the concept of interactive structural hierarchy in materials, acknowledging that there is an intrinsic complexity to real materials, for which he advocated we should be taking a systems approach. The same framework of systems engineering that's used across all other engineering fields, we should be applying our knowledge of materials and treating materials themselves as systems. And so we've taken that to heart. And in implementing it, a very important concept has been what the late Morris Cohen described as a reciprocity between the opposite philosophies of science and engineering that is represented by this three-link chain structure in which the deductive cause and effect logic of science flows from left to right, the inductive goal means relations of engineering flow from right to left, and this specific linear logic has allowed us to put those opposite philosophies together in a non-turbulent, efficient way. We use this as the backbone of a system representation of the material, to which we then add Smith's view of structural hierarchy, so that each design project begins with this type of a system chart. So this is to represent what the material is, and to start with trying to get the entire material on one page to make sure we don't miss anything important. So what this shows is the combination of properties that determine the performance of the material in service, those properties can be mapped back to a hierarchy of microstructural subsystems that dynamically evolve throughout the stages of materials processing. And this then allows us to identify and prioritize the structure property and process structure links for which we want to build predictive design models. Now, at that point, we could build relatively superficial empirical correlations. The opportunity, though, the much more predictive capability is to use our mechanistic knowledge, made quantitative by these fundamental databases, to build science-based predictive tools that can go beyond interpolation to really predict bigger changes in the attributes we need to control in the materials. So that was the concept from the start. And this, of course, motivated a lot of research in the 1980s to make our scientific understanding sufficiently quantitative to implement this. The models that have come out of that we used are summarized by this hierarchy, which is integrating material science, applied mechanics, and quantum physics. So at the deepest level, as I mentioned earlier, the DFT methods have improved in their accuracy, where they are allowing us to directly predict fundamental thermodynamic quantities. And where that's been most useful is in surface thermodynamics, which is the most difficult to measure. So that's given us direct predictive control of a number of surface phenomena. Where the material science is most quantitative is in the theory of both precipitation and precipitation strengthening, which has allowed us to treat our strength goals as constraints within the design. Where the applied mechanics fits in is the simulation of various unit processes of fracture, which give us new structure property relations to set new microstructural objectives in design. And it's really these three levels here that define our meeting performance goals in the design. Equally important is materials processability, and that's addressed by our models of phase transformations, the solid state phase allotropic transformations, as well as the liquid solid transformations, which are really the most scale sensitive parts, which are very important to process scale up. The ability to model that up front means that we can constrain the design of a material for the final scale of production and eliminate empirical scale up. And again, how we bring this all together is through a kind of parametric design that's deliberately structured to exploit the capabilities of these fundamental databases. An example of the research that we undertook, this is a thorough study of the precipitation hardening behavior in what was the highest performance steel of the time back in the 1980s. This research was actually undertaken under a 1989 Air Force nanotechnology program that allowed us to bring together a wide array of experimental techniques of the order of 10, including small angle neutron scattering. And this allowed us to then map out in detail the evolution versus tempering time of particle size, particle shape, number density and phase fraction, the evolution of the lattice parameters of the carbide phase and its composition trajectory, and the evolution of the hardness and strength. And what this thorough characterization allowed us to do is to validate the theory of precipitation at high supersaturations, which allowed us to parameterize that precipitation behavior, in which thermodynamic driving forces control particle size, and diffusion rate constants determine the time scale. And then this enabled a parametric approach to the design of a precipitation strengthening efficiency in these steels. With those methods, we've been able to design steels that for a given carbon content are 50% stronger than the previous steels. One of the most ambitious problems was intergranular stress corrosion cracking due to environmental hydrogen interactions as affected by the prior segregation of embrittling segregants. And a very important contribution early on in the program was the work of Rice and Wang at Harvard, who developed a surface thermodynamic description of interfacial embrittlement by these components, where the embrittlement potency scales with the difference in the surface segregation energy between a free surface and a grain boundary. Initially, unique to iron, there was enough data to actually test out this correlation that the surface thermodynamics had been measured. We went on from that to then correlate the same quantity to the energy differences that we predict from our DFT calculations, and showed the ability that we could correctly predict the relative embrittlement potency of phosphorus and sulfur and the cohesion enhancing effects of boron carbon. Now, less well known at the time was the role of the substitutional alloying elements. So the same methods were used to predict the effects of substitutional elements for a handful of cases with the rigorous calculations, used that to calibrate a simplified model that then made the projections here, allowing us to identify the largest negative numbers, which are the strongest substitutional cohesion enhancers. This was then validated with the more rigorous calculations. This was then used to design the first of what we've called our quantum steels, where by designing new compositions to control grain boundary composition, coming directly from a quantum mechanically predicted genome, we have completely eliminated the intergranular mode of stress corrosion cracking in these very high performance steels. The way that's all put together is by this type of parametric design. Here's an example for the stainless landing gear steel of a cross plot for a couple of composition variables of the parameters important to the strengthening efficiency. The thermodynamic driving force shown by the yellow contours is important to controlling the particle size, and then that in combination with the phase fraction determined by the carbon content leads to these predictions of the peak hardness we can achieve in tempering such a steel. And then superimposed are the constraints for processability of the martensitic transformation temperatures need to be high enough to get a fully martensitic microstructure. And then there's a constraint of the solubility of the carbide formers, which gives us these contours of solution temperatures. So this is then the final stage of structure in the last stage of tempering that determines the final strengthening potential of the steel. Backing up to earlier stages of processing, this is an optimization of a composition variable and process temperatures where we're optimizing the grain refining dispersion that has to be present at the solution temperature to maintain the grain size we want. And there, we're constraining the solubility of that phase so that we can put it into solution at homogenization temperatures, precipitate it during hot forging, and have it have the right phase fraction and size during the austenitizing temperature to give us the grain refinement required. So in a similar way, we can map the requirements at each stage of processing and the level of microstructure that that stage of processing controls, and through this type of graphical parametric design, satisfy all of those conditions. Using the kind of graphical design, also the contours give us a sense of the sensitivities so that we can also practice a robust design strategy and minimize the intrinsic sensitivities to variation in these solutions. So this has yielded the first four commercial steels represented on this chart. In addition to the stainless landing gear steel, we have a high toughness steel for carrier-based applications that's been flight qualified. And we have a pair of very high performance gear steels doing well in off-road racing and on-track racing, and currently being qualified for helicopter applications. All four of these are using that efficient strengthening through the control of the carbides, in which for all of these cases, the carbide size is optimized at this 3 nanometer size as validated by this 3D atom probe reconstruction. Now that's the achievements of the design process. This is a summary of the normal process of empirical development, where on laboratory to small scale, we will find prototypes that meet our requirements. We would then start experimental scale-up and the process optimization at the component level, and ultimately measure manufacturing variation so we can specify minimum property design allowables. The process of materials design really only itself impacts this first leg, which amounts to only 10% of the time and cost of getting material to an application. So it was the goal of the DARPA AIM program starting in 2000 to look at, based on the success of the methodology demonstrated here, what is the methodology and tools that can address the rest of this cycle that would really have the impact. And our opportunity under the AIM project was to do this in collaboration with Pratt & Whitney and GE in the context of aeroturbine disc alloys. And this introduced us to the architecture of computational engineering of aeroturbines, where all these different tools of macroscopic behavior and processing are linked together by the eyesight process integration design optimization software system. What was necessary under the AIM program was to build a microstructure simulator, PrecipiCalc, that we could then link to heat transfer simulations to map the evolution of rather complex microstructures in response to the thermal history as a function of position in a turbine disk. Whoops. Under that, and we also had to calibrate and validate structure property models that were implemented as analytical functions, and that was done in a spreadsheet. So really, PrecipiCalc was the new numerical simulator that we had to have to enable this technology. After calibrating against existing turbine disks, a demonstration project was done where a subscale turbine disk was designed using these tools and tested to overspin failure to validate the performance predictions. But it also gave us the opportunity to section companion forgings and validate the predicted spatial variation in the forging of microstructure and properties, where we were able to predict that spatial variation well within part-to-part variation. Then that sets the stage for what was the most ambitious challenge, was the early forecast from limited data of the distribution of properties, in this case yield strength, that would come from the allowable variation in process specifications over 6 stages of turbine disk manufacturing. The strategy we developed there was to use our mechanistic models to get the shape of this cumulative distribution function, and then use limited data to recalibrate that by linear transformation only, where the idea is limited data can only inform the first 2 moments of the mean and variance and cannot define shape. So what we need from science is the prediction of the shape of the distribution. Limited data can give us that final calibration to give us accuracy. And so we're able to demonstrate that for the forecast of the 1% minimum property represented here, which is the A-basis design allowable, that normally takes on the order of 300 experiments, with as few as 15 experiments, and shown here for room temperature, we can take the raw simulation, recalibrated by only 15 data points, and within 1 KSI get that 1% minimum property. This is the same exercise for the high temperature property. So the DARPA AIM initiative, using the case of a turbine disk where we already had the answer, demonstrated that through these techniques it is possible to get the accuracy of forecasts we need so we can specify the design allowable much earlier in the process. Now, as I mentioned, it was the 2004 study that was specifically focused on this kind of technology acceleration and best industry practices, and concluded that the best was, at that time, what had been achieved in the DARPA AIM program. Now, there's been a lot more attention given to this 2008 study that coined the term integration computational materials engineering. But this actually cited examples that wasn't about new materials. It was about better application of existing materials with models. I think as well that to generate broader interest in the technology, it kind of set the bar low in terms of what some of the industry practices were under this umbrella. It unfortunately created a sense that this technology is rather immature, where ironically, the earlier study actually emphasized the maturity of the technology. But I think another important characteristic of this study, and there have been now about 7 National Academy studies pointing to the potential of this technology, it was the 2004 study that uniquely really called out the leading role of the network of small businesses that have actually created and maintained this technology. And so this is a summary of where we were a decade ago in terms of the companies and the softwares and database systems that they've maintained to really generate this technology and continue it. And I would say today, this is still where the forefront is of this technology. Let's see, okay. So the stainless landing gear steel I described earlier was actually brought into the DARPA AIM program. It was designed concurrently with the creation of the AIM methodology. It was brought into the program to be the first demonstrator of the application of this method to a new material. And under follow-on funding from DARPA, The goal was to take the data we would have from 3 production scale heats of the material to make an early forecast of the 1% probability A basis allowable that ultimately has to be statistically demonstrated with 10 full-scale production heats, which is a lot of expensive inventory of steel. This shows the predictions that were made. So that with those, the blue curve is the Monte Carlo simulation of the shape of the function. This is the calibration of the first 3 heats. This then is the final validation where we meet all the requirements of the 10 heats. And once again, we got that 1% probability value within 1 KSI. In this case, in order to be a drop-in replacement, it was vitally important that we match this 280 KSI minimum number that allows us to replace the existing steel without any design changes of the components. In practice, at the level of 2 heats, these forecasts were able to show that we were at risk of not meeting that quantity. And so we were able to re-optimize the processing very early in the qualification program and save a lot of time and cost to meet that requirement. The Navy's been the largest supporter of this technology. And in fact, so this was a slide we put together during one of our Navy projects to show the range of applications of this technology that Questec has undertaken specifically for the Navy that cuts a broad range of not only different alloys, but even some ceramic systems as well. This is our scorecard on the technology acceleration. So what this represents is the technology readiness levels at the level of the landing gear. This is the corresponding materials development milestones. In the case of the stainless landing gear steel, it was a very ambitious goal. It took about 5 iterations of design. The AIM methodology was developed by about this point here, and you can see that things then accelerated after. We made it from a clean sheet of paper to material level qualification in about 8 years in that case. For our high toughness steel, for the carrier-based applications, we had sufficiently improved accuracy in our databases and tools that we got it right on the first iteration. So you can see we got a faster start. We made it from a clean sheet to material level qualification, in this case, at 6 years. So we're really meeting the goals set for the Materials Genome Initiative with these examples. More importantly, is having done it once before, while we were doing this, it was possible at the level of the first 3 heats that the Navy had enough confidence in our forecast that they went ahead with a manufacturing technology program to apply this new steel in the hook shank application for the carrier-based planes, basically the tail hook assembly, which is a very critical component, and start that manufacturing technology optimization early enough that it turns out that within 1 month of getting material level qualification, we actually had component level qualification by the ability to make that engineering decision much earlier. So it's not only that we're compressing the materials qualification cycle, we're also compressing the full application cycle through this. Now, both of those examples are from the viewpoint of compressing the materials cycle under conditions where we're trying to be a drop-in replacement. We don't want to change the component. We don't want to redesign. That would slow things down. I think the ultimate impact of this technology is the opportunity for concurrency. Just about all other branches of engineering except materials are able to work together to accelerate the full technology development cycle, and that with this acceleration of materials cycle, we can then become a part of that and look at the value of the concurrent development of materials and structures. And where we first explored that a decade ago is in an upper undergraduate interdisciplinary design project course, where we were able to draw on 2 channels of Navy-supported research at the university. One was novel panel structures for weight-efficient blast protection, and the other was new steels we were designing for blast protection. And in the context of anti-terrorism blast mitigation, This team, for the first time, looked at taking those simulation tools for the study for the structures, plus the new properties we projected as designable, and put those together. And it forecast what performance could be achieved, but most importantly, it actually redirected the materials design work to meet new property objectives, and that research is still underway since then. As far as the highest achievement in that kind of concurrency, the best example is what was announced in September in the Apple Watch. It's not unusual that Apple does market their materials as part of their products. This is the first time that Apple marketed their own materials. And so there actually were 4 new alloys with very significant performance improvements that were announced with the Apple Watch. It turns out that those ambitious property achievements the materials were created and fully integrated into the product in just 2 years from acquiring the technology to do it. Now, the AIM project, we found that relative to standard metallographic characterization, we were predicting microstructure at a level of precision that exceeded the accuracy of standard metallographic microstructural characterization. And that helped to make the case for the 5-year ONR DARPA D3D digital structure project that ran from 2005 to 2010. And the idea was to bring together the tomographic tools that could do for materials what the CAT scan has done for medicine, to really thoroughly characterize real microstructure in 3D rather than trying to infer these quantities from 2D. And so in this, we brought together, at that time, a suite of destructive tomographic techniques at the atomic level, from the atom probe up through the focused ion beam SEM level characterization, and then serial sectioning and light microscopy, going from the nanoscale level important to strengthening, submicron and multi-micron scales important to fracture toughness and fatigue properties, and to use this higher fidelity information to inform a next generation of 3D simulators of microstructure in processing and in service. And I'll come back to that a bit later. Meanwhile, back at the university, we've developed a 9-month ICME master's program where we are teaching first the methods in this set of core subjects up here, and then finally the students who participate in this get a project started in the fall that culminates as an integrative design project in my materials design class in the spring quarter. And for those who are interested in other techniques, we have an array of possible electives. So it is possible to get a good sense of not only the tools, but their integration within this 3-quarter sequence. In the design class, this is a summary of the courses we ran last spring. These happen to be largely in metals areas because that's where the funded research currently is. Every one of these projects is drawn from funded research for which there is a doctoral student or postdoc who can serve as a coach to these design teams, which is particularly important for the undergraduates to bring them to the kind of technical level that's essential to meet these kind of projects. It was this project here on a high-performance shaped memory alloy that was the latest winner in the ASM National Design Competition. Whoops. Meanwhile, we have this National Network for Manufacturing Innovation. As we've rediscovered manufacturing in the United States, we now have 4 of these institutes, and the most recent are the Detroit-based Institute for Lightweight Metals Technology and the Chicago-based Digital Laboratory for Manufacturing. And Northwestern and Questech are involved in both of these institutes. Case of the lightweighting metals, it was a chance for our Questech CEO, Aziz Asfahani, to go to the White House, where we had to take this quote from the president. The I won't go through the details of this, but these are fairly large-scale programs that between the federal funding and the industry matching, it's $140 million over 5 years. So these are very significant investments in manufacturing technology. It is to look at late stages of the manufacturing technology development, but it's very much in the same spirit of what we're trying to do in the acceleration of the material cycle. And on that, the Materials Genome Initiative was conceived to support the broader manufacturing initiative. And really what amounts today to, as the lead center in the MGI is this NIST-funded Center for Hierarchical Materials Design that just started at Northwestern in collaboration with Argonne. So in fact, this is the first major initiative under the recently formed Northwestern Argonne Institute. This is funded for 5 years at $30 million and extendable for a second 5 years. Peter Voorhees and I are co-directors at Northwestern, with Juan de Pablo at University of Chicago as a co-director. And the idea is to not only improve the overall methods, tools, and databases, but to expand the scope of this methodology and to demonstrate a general methodology that spans metals and polymers. So that's not only Northwestern, Chicago, and Argonne, but Questec is a partner in this program to further develop this AIM acceleration technology so that we can demonstrate taking the materials out of this center all the way to application. The actual approach we've taken is that all of the development of tools and databases are driven by the use cases in both hard and soft materials. And that then drives the full suite of database systems that are being developed. We have 2 levels of precipitation hardened alloys. We have eutectic reinforced silicon-based composites. And then in soft materials, a number of projects including biomaterials. This is the overall scope of the center activities, where the top level is the overall technology of materials design and AIM accelerated qualification, which is represented by these 2 levels here, both of which are supported by the mechanistic models of process structure and structure property behavior that, again, are structured to be made quantitative by the fundamental CalFAD thermodynamic databases. Shown in yellow is the hierarchy of databases that are under development through this center. Right now, the database, one database that already exists is the database of materials properties that is searched in material selection by the Granta search and selection system. And of course, that's where we send our output design allowables today. Below the level of the existing CalFAD phase level databases, one of our primary database activities is building a pre-CalFAD protodata repository that will be hosted at NIST, which is where we send the raw data of tie lines, phase relations, calorimetry, and DFT predictions. That is the raw data we use to feed the CalFAD assessments. So that's under construction, and the place where we're sending the fundamental data right now being developed. Under the D3D project, from the tomographic work that was done, a prototype database was set up. We're collaborating with ASM to rejuvenate that database and develop it further. And long term, where we're looking to go in the second 5 years of this effort is ultimately replace what is descriptive constitutive laws that actually limit the accuracy of finite element codes at the component level. We'd like to replace that with microstructural state variable constitutive law databases that are connected to the simulators of microstructural evolution, so that we can hand off to the macroscopic world much more realistic representations of materials behavior and get that much more out of digital engineering capability. The other thing we're exploring is to take the same architecture of the search system developed by Granta that searches material properties for selection at the higher levels use the same strategy to query these databases and select components and phases in the process of design of materials. So I think I have time. Yes, I do. One of the new capabilities we're exploring is the opportunity of high throughput DFT calculations. So making large numbers of relatively small calculations with the current supercomputing capabilities. Chris Wolverton's been collaborating with us. Here's an example where he's developed hundreds of thousands of compounds and predicted their relative phase stability and other attributes that can help us during materials design to assess the feasibility of alternative compounds that could perform better than the phases we're already using. This is an example of that expanded search capability, where currently the Ashby materials selection system is to use these cross plots of materials properties to select them. Here's an early example we did in the design of an oxidation-resistant niobium alloy, where in a similar vein, we're looking here at cross plots of thermochemical and thermophysical properties of potential oxide scales, and then kinetic properties of parabolic rate constants and relative diffusivities in the substrate, so that we were actually able to identify yttrium aluminum garnet as a multi-component scale that could give us an oxidation-resistant niobium alloy, and we're able to actually implement that and demonstrate it. So this is the type of thing that we want to do more of. The other area that there's a lot of interest in today that's come out of the realm of big data is data mining practices. What we're looking at here is one thing is, where are the opportunities where for materials data gets large enough to be worthy of applying these statistically based mining efforts. But the other issue we're looking at is, unlike some other fields where there's very little mechanistic knowledge to be an alternative to empirical correlation, the fact is in materials we have a lot of knowledge, and so we are exploring ways to modify these methodologies. So instead of assuming total ignorance, we use not only data, but we take the mechanistic knowledge we have to transform that data before we mine it. And so one of the demonstration projects we actually ran in an undergraduate class last year was to use a fatigue property database from NIMS in Japan, which had about 400 different alloys, their composition and processing, and their final performance, to translate that information with the CalFAD thermodynamics into structural attributes, and then mine that. And we were able to show, compared to the brute force approach, we could get a more accurate representation of the process structure property relations. In the use cases, we have a large activity in precipitation hardened cobalt alloys, and one of the places where, in addition to going after very high performance cobalt alloys for aeroturbine applications, Questech has already designed for low temperature alloys a new bushing alloy to replace beryllium copper. And this is the area where we're applying the AIM methodology and demonstrating and improving that methodology to accelerate the process optimization of this new cobalt alloy. We're doing very similar things for medical applications in designing higher fatigue performance shape memory alloys that can enable these kinds of medical devices. And here's an example where we have built out during the D3D project a micromechanical fatigue nucleation simulator, which we've demonstrated in the steels. We're now doing the same thing in the shape memory alloy. And here's an example of the predicted improvement in allowable strain amplitude we can get at a life of 10 to the 9th, which is very hard to measure. The kind of improvement we can get by getting a 50% strength increase by bringing in nanodispersion strengthening into these shape memory alloys. So where I'd like to end up with is, again, the last major project we completed was this D3D project. And to show you, and I should comment that in 2005, to assess the feasibility of using these tools, our focus was on destructive tomographic techniques. But we've done some follow-on work based on what we were able to demonstrate with these techniques, and we have a number of projects with the APS now using X-ray tomographic, virtual tomography to further enhance, in some cases, explore much larger volumes of material to look at sparse microstructural features. So I think we've demonstrated how good quantitative tomography can impact our predictive capabilities. And one of the reasons I was happy to come here and meet with people today is to explore with the advancing applications, the advancing capabilities, particularly the combination of sample volumes and ultimate resolution that's going to be achievable with these tomographic techniques, we think is going to be an important additional contribution to what we're doing under the Materials Design Center. But to show how all this fits together, the Navy actually asked us to put together a movie, which we did. Let me see if I can get this to go. Oh, here's what I need down here. So actually, if I could have the lights dimmed for movie theater effect. Whoops, is this it? Goes away. Yeah, go ahead. You got to be a bit quicker. You got to get that one. Okay, we're at full screen, right? We tried to conform to Hollywood standards in putting this together. The space you are flying through is the submicron titanium carbide grain refining dispersion in a 4330 modified martensitic steel. And that's shown with a little better resolution. This is from FIB-SEM reconstruction, where the white particles are the titanium carbides. Also shown are the primary titanium nitride inclusions, and very importantly, the interfacial damage inherited from prior deformation processing. Our micromechanical fatigue simulations show that this is a particularly important attribute in the nucleation potency for fatigue. Now, zooming in down to the local electrode atom probe, this is a reconstruction of the nanoscale copper and carbide strengthening dispersion and a blast protection steel that we designed for the Navy. The new information this is giving us that we didn't have before is the spatial distribution of these particles. We're simulating that now for the coarsening of the copper particles in a 3D simulator that allows for the diffusion field overlap. And then we're taking statistically equivalent spatial distribution of these particles, putting that in a dislocation simulator, and measuring now the impact on strength of these new attributes that we're getting from tomography that we didn't have before. So to get greater accuracy out of our strength models by taking this into account. Now, moving up to those submicron particles, here what we're interested in is the interfacial adhesion and how it affects fracture processes. And here we've been able to scale up our DFT all-electron calculations to look at a semi-coherent interface between iron and titanium carbide and calculate the work of adhesion, where we find that it comes apart first at the dislocation before spreading to the coherent patches, thusly. That then gives us the work of adhesion that we can put into continuum simulations of the microvoiding process of these particles. Which we simulate here. So these particles are allowed to separate at interfaces. It gives us this stress strain curve where the microvoiding is driving softening, that in turn drives the shear localization and describes how the material goes all the way to shear fracture. Now, the way we validate that is we're taking the material under a linear shear test to the onset of the formation of a shear band, and then by fib SEM reconstruction, cutting out that shear band. And here, shown in red, is we're able to capture one of the first clusters of those microvoids, very similar to that simulation. You can see as we rotate it around, the primary inclusions are also cracked by the principal stresses. And you can also see the anisotropy of this dispersion and how things line up when we look down the forging direction. Now, the context of this we're interested in is 45 degrees away in the context of the process zone of a mode 1 crack tip. And there, we've taken these crack tips apart by serial sectioning and by light microscopy reconstructed the process zone at the head of this, where you can see the partially intact material has a corrugated washboard type of structure that's coming from the shear localization from the fine particles accelerating the coalescence of the primary voids. We simulate that by putting in a statistically equivalent array of the primary voids embedded in a matrix that has the homogenized constitutive law coming from the submicron microvoiding, and find that we can not only predict the COD toughness, but the actual wavelength of this pattern of shear localization. And so we're well on our way to predicting fracture toughness as accurately as we predict strength. We hope. All right, and this is what we hope to be able to do better with the APS. Thank you for your attention.
About materials, movies, anything?
Need a material?
Mine is off. Oh, mine's on.
So I guess what's very important, what we can do is validate some of these models. So in the data that you're showing, I guess you're looking for some validation, and then would you think of that as kind of giving an extra weighting factor to the models if it's validated versus not? Is that something you've been thinking about?
Yeah, I didn't really emphasize it, but uncertainty quantification is essential to this technique. So from the start, we've had to bring together the instrumentation that allows us to really calibrate and validate these predictions. So any of these model predictions, we do have a good assessment of what the uncertainty is, which helps us a lot too to know where we need to make improvements and where we don't need to. I would say particularly the more sophisticated instrumentation, it's not just the validation, but the calibration, getting more quantitative information. Some of it is in terms of the mechanisms of things. There are qualitative questions to ask, but more typically it's moving on to making that information sufficiently quantitative that it can help us with the quantitative engineering.
Any measurement of radiation damage? Can you study how materials can be strengthened against radiation damage?
We've done some work on materials that would be used for nuclear applications as well as other applications. One of the things we've been exploring, very similar to the way that we manage hydrogen in our stress corrosion resistant steels, we are looking at ways that we could manage helium in things like materials for first wall applications and fusion, of actually designing compounds that could actually absorb helium in their volume rather than just depending on interfaces, that kind of thing.
So I assume you have all the tools ready, you just have to simulate a beam hitting
Yeah,
some
I
atoms,
think,
suppose.
yeah. I think there's enough known about radiation damage that there is a lot of opportunity to design for it. Yep. Yep.
Yeah, your example of the Apple iWatch I thought was really interesting. You said that only within 2 years they actually got from what they wanted to actual production.
Yep.
Was that actually something that somebody had designed to get 40% higher strength in, the materials that they were actually doing, the 2 years, did that include the design from a computational perspective, or was that just serendipity? Or
Yeah,
I
these
mean,
are
it
all-
seems very,
yeah.
very short, right? 2 years.
Yeah, I
To
mean,
me, it seems really
yes.
short to get into production mode.
Yeah, it shows what can be done when a
When $1
major
billion
corporation puts significant resources
Was
behind
it computational, or was it like, trial and error, or?
It was using the very technology I described.
I see. Okay, so it really was starting from computational materials design.
Yeah, that is how they were doing it. And so it was a very good example of concurrency, where as they were developing that product, they saw for the different variants they wanted to have, they designed it to use the cold work stainless steel as the main body. And then the idea was the sport watch is going to be in aluminum, but you've got to have an aluminum alloy that can meet the same specific strength to be that structure. Similarly with the gold watch, it's got to have also has to be strengthened to that level for the primary structure as well as to be more scratch resistant. So the idea that they could make one structure and have a diversity of different materials for the different variants that met all the same mechanical requirements was some pretty ambitious objectives, and it was all achieved by precipitation hardened alloy systems using these methods.
And who actually did the research for that? It wasn't Apple themselves, right?
Apple acquired the technology to do this.
I see. So they bought up some companies that were.
And I cannot confirm or deny the rumors as to where they bought it from.
Any other questions? Okay, let's thank Professor Olson one more time.